Hi Ashish, can you listen me?
Yes, yes, I can listen you.
Okay, so welcome once again. Uh,
Thank you.
I guess we can wait for 10 minutes.
Sure.
Let other people join, then we will start.
हमें तीसरी भाषा क्या है? ये साले मानो चुन ये लिख रहे हैं aliens name अरे मारवा होगा ना alien मेरी धरती मोयो गबाबू
अब बताओ अभिषेक। अभिषेक,
कुछ बोल रहा है क्या?
हाँ हम तुमसे ही पूछ रहे हैं, तुम्हारी शकल बीच बीच में आ रही है ना। देखो तुम पूरे फ्रेम पे हो, ठीक है, कुछ बकचोदी नहीं करना, पूरे रिकॉर्ड हो जाओगे, ठीक है।
वो है म्यूट है
मूड तो है, तभी तो बतिया रहे हैं।
तो बढ़िया लगा ना बैकग्राउंड,
हैं?
बैकग्राउंड अच्छा लगा ना।
का ये अच्छा नहीं है क्या?
नहीं मतलब ऐसा लगा कि पीछे दिखे ही ना।
अबे वो तो आता ही है, वो तुमको फोकस करता है ना बार बार। अब देखो अभी दोनों लोग दिख रहे हैं, देखो ये बकचोदी करते हुए। सर जी, सर जी, अबूर सर, वेज बिरयानी किस दिन खिलाओगे बताओ?
मैं बना
हैं?
कौन सा मैं पे पॉइंट बदल गया ना ये, बता रहा हूँ।
डिस्ट्रैक्ट हो रहा हो, बताओ।
कंट्रोल मैप के साथ पॉइंट। ये सर है मेरे पास ये सब, करूँ ये वो सब है कंटूर वाला। कंटूर नहीं मतलब वो डेप्थ वाटर टेबल स्केल 0.2 से 2.8 से 5.3 5.6 ये कैसे बनाया? कुछ करना थोड़ी ना बे। अच्छा इसका कंटूर है, कंटूर नहीं है ये, इंटरपोलेट किया है बस IDW करके। अच्छा ये उसने बनाया होगा। हाँ अच्छा यही मान रहा था वो, पता नहीं लगता ये खुद बनाया है, वो मेरे को नहीं पता भाई ये चीज मान रहा हूँ मैं। अब मैं क्या करता हूँ ना, इसको रिप्लेस करता हूँ जो तूने जो मुझे टेबल दी, ठीक यही करना है ना। Take some groundwater and learn what during एक हफ्ते लेंगे इसी पर हैं? आप ले रहे हैं थोड़े, अभी तो डेटा नहीं दे रहे, अगले मंगलवार को देंगे।
हेलो आशीष,
Yes.
I want to know like which assignment have you submitted recently?
Assignment number 1 we have submitted.
Okay, and what about the assignment 2? What is the deadline?
Deadline is tomorrow.
Okay, deadline is tomorrow. That's fantastic. Good.
Yes.
So Ashish, I want to mention few points like okay, Bala Murugan, you have submitted both the assignment. That's fantastic. Good. Nice to know this. So I want to mention few things like today, whatever the things we are going to discuss,
Mm.
it will be mainly focusing on numerical parts. So we will be solving numerical problems more as compared to the basic theoretical concepts. Though we will add those theoretical concepts in numerical problems. So I guess there are hardly 8 to 10 numericals are there.
Mm.
So today we will be more oriented with pen and our notebook. Okay?
Sure, sure.
Yeah. So I guess should we start or I want like I think we should start now, right?
Mm.
Okay, I'm just sharing my screen now. kindly confirm whether my screen is visible to you.
Yeah, it's visible.
Okay. So, welcome once again for the assignment session 2 on NPTEL course Engineering Hydrology. So, today's discussion will involve some important topics like atmospheric water. We will try to figure out some questions related to atmospheric water, like how the atmospheric water circulation takes place in our atmosphere. Then coming to the second part, that is a water vapor. So how there is a difference of humidity as well as the pressure variation, due to which vapors are forming, and then again simultaneously it is getting condensed and converted finally into the form of precipitation. Again, there will be one or two numerical part which is just summarizing the our last topic, that is residence time. Then we will discuss some numerical parts related to terminal velocity as well as the humidity. Then there will be one major numerical that will associate that how we can quantify the amount of precipitation that could be taken place if there is certain kind of parameters we have, then how we can quantify those. So let's start. So coming to the first question, so here you can see, before going to this, again I will invite both of you to answer these questions first, then we will discuss that what would be the possible explanation associated with this. Okay, so the first question is, these are the regions of high pressure, usually of large areal extent. So this is related to a certain kind of precipitation pattern which influence our Indian region. So what could be this? Like first one is anticyclone, then second one is frontal boundary, then control surface, and hurricanes.
Yeah, it's anticyclones.
Fantastic. So good one. I want to also know that if we are counting a cyclone, then what would be the pressure? Like, it will be a high pressure also only, or maybe it will be a changing, or maybe a variation is there if we are counting the cyclone, because in Indian region we are mainly concerned with the cyclones, right? In India we mainly face cyclone problem. And can you tell which part of India suffer more cyclone events, like
Yeah,
Arabian Sea region that is there, or some other boundaries there related, which is nearby the
both
Bay of Bengal.
Bay of Bengal and Arabian Sea, both I think.
Yeah, good one. Okay, so good one, Ashish, that the answer is anticyclone only. Okay, so the some basic points that we should know before leaving this question. So these are the regions of anticyclone are the regions of high pressure, usually of large areal extent. The weather is usually calm at the center. Okay, so center is related to I, that we call. Okay, anticyclone cause clockwise wind circulation in the northern hemisphere. Okay, so you may have heard, if cyclone word is coming, then definitely for the northern hemisphere we are dealing with the anti-clockwise wind circulation is there. Okay,
Okay.
so if there is certain kind of cyclone is happening, so there is a I. So here you can see a low pressure region. Okay, and if we are low, if there is a low pressure region, then definitely it will be counting a high wind velocity. So here you will experience high wind velocity, and as we are moving away from the eye, then we are having low wind velocity. Okay, and these cyclone can have maximum velocity of something 250 kilometer per hour. It can go up to this, and it can cover an area of something, maybe the coastal area, which is of about 20 to 25 kilometers of a stretch in the coastal. Okay, then winds are moderate speed, and but if you are talking about the anticyclones, then definitely it is of moderate speed, so definitely it will be counting in terms of 90 to 100 kilometer kmph only. And the outer edge and at the outer edge, cloudy and precipitation condition exist. Okay, so definitely we know that whenever the cyclones or maybe anticyclones are forming, so definitely there is a wind carrying the clouds to the inner area, like inland area, and then precipitation comes at that location. Now the next question comes: orographic precipitation occur due to air masses being lifted to higher altitudes by. So firstly I want to know, have you heard of this orographic precipitation yet in your lectures?
Yes. Yes.
Good one. So can you answer this?
The presence of mountain barriers.
Good. Yes. So presence of mountain barriers, that is a good one. Can you answer a kind of precipitation that comes due to density difference of air masses? Can you tell this?
I think this is the first form of rainfall variation. Frontal.
Not frontal. I guess yes, definitely it will be a frontal. Yes, right.
Yes.
But it can also due to a convection also, right? If there is a localized heating is happening, then definitely this warmer air will be getting upward. Okay, and density difference will cause in the air masses. So yeah, definitely you are right that this is caused due to the presence of mountain barriers. Okay, now can you tell me one possible drawback of orographic precipitation, that we don't want orographic precipitation in our region? Can you tell? Sometimes people used to say that this is we are getting less or high precipitation, a kind of problem exists due to orographic precipitation. Can you tell what could be the reason?
Due to high rainfall.
No, orographic precipitation is basically you just mentioned the point that this mountain barrier, they are causing orographic precipitation, right? So if there is one kind of mountain is there, so definitely whatever the air masses is it is rising, they are getting they are getting attract what I say yes, they are getting reversed by this, obstruction in their movement, I should say. Okay, so now whatever the things it is getting in the upward direction, they are directly falling the water here in this region, but these air wind the wind that is carrying the water vapor, they are not crossing this particular region, right? So what would happen, that there will be a scanty of rainfall in this region. So because of this, we always say that at the leeward side we don't get enough amount of precipitation, and due to which drought kind of situation of sometimes we used to face in these regions. Okay, got it? So we will see this orographic precipitation. So moist air masses may get lifted up due to higher altitude due to the presence of mountain barrier, and consequently undergo cooling, condensation and precipitation. Good one. Now such precipitation is known as orographic precipitation. Thus in the mountain ridges, windward slope, there would be two kind of slope that we have to see. while we are studying the mountain ranges problem. So there will be first one is like this one, windward slope, and there again there will be another one that is a leeward slope. Okay, so leeward slope they are causing a light rainfall, right, and windward slope they are causing heavy precipitation. Okay, Ashish?
Yes, yes, I got it.
Okay, now moving to the next question. So question is, dash of a mountain range typically receive the most precipitation. Now again the
Windward,
same thing. Yes, what you say?
windward slopes.
Yes, windward slope, good one. So this is the answer. Yes, leeward side will be receiving scanty precipitation, like some kind of drought like of situation can occur in those regions. Okay.
Mhm.
Okay, we are moving to the next. Okay, explanation. So here you can get the better picture that what is actually happening. Okay, so in the orographic rainfall, windward slope of the mountain receive maximum rain, and the leeward receive remain generally drier and is known as the rain shadow area. This is important. You should underline these particular word, rain shadow area form. So this is the area where rain shadow phenomena exist. Okay, now coming to the next question. So atmospheric circulation or the movement of water vapor along with the wind is due to, you might have got this particular
Yeah,
aspect in your
it's the
lectures.
rotation of the earth and heat transfer. 1 and 3 is correct.
Good one. So both these points are correct. You are right. So rotation of earth as well as the heat transfer between the equator and poles, they are causing the atmospheric circulation, or in other terms atmospheric circulation is just like a movement of water vapor along with the winds. So we can see the explanation is that the poles are very cold, right? Poles are very cold because at that time what is actually happening, sun is very far from these poles. Okay, at the equator sun is just uphead to the equator, so it is very near. Okay, and due to the difference in the heating, okay, transfer of heat energy takes place along with the formation of some depression currents, with winds taking place from one place to another. The movement of moisture in the atmosphere take place. Okay, Ashish?
Yes, correct.
Okay, so wait a minute.
29 locations they were.
Scott, I should see maybe Bala Murugan have replied some more questions. I should.
He is replying.
Okay, good one.
31
Okay, Bala Murugan, fantastic, good, good. Non-uniform rainfall. Okay, good.
those were discarded in the 29.
Okay, Bala Murugan, good. Okay, we are moving ahead.
Discarded the
Okay, so I guess there was a few questions only. So we are moving ahead. Maybe in between we can take some rest in between. Okay. So coming to the question related to the residence time once again. So we have discussed like a few hydrological parameters in our earlier session related to river as well as the atmospheric water, right? So now the question is what? That we have to quantify the average duration of the particle of water to pass through a phase of hydrological cycle. Okay, so we have to arrange this. So we know that ocean is one source of water availability, groundwater is another source, river is there, and atmospheric vapor is there. So we have to arrange them based on the residence value. So Ashish, in our previous class we have quantified the residence time value for the atmospheric vapor, that how much time it is taking. Okay, how much time a particle in the atmospheric vapor is taking
The
to pass.
less. Yes,
So
yes.
what was its value I guess someone is.
Yeah, it's I think ocean, global groundwater.
Wait a minute. Okay, Balamurgan is replying. Anyone is joining or something, I guess.
At
Ashish, if you get anything like anyone is requesting or something, do you got anything?
no.
Okay, no issue. I guess no one is there.
Yeah.
Huh. So Ashish, do you remember for the atmosphere?
Yes,
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 Balamurgan
yes.
replied that atmospheric water we have a residence time value of something 8.2, right? 8.2 it was in days, right?
Yes, yes,
For the
yes.
river we have also computed that TR value was having of about 20
But
or maybe 22, right?
yes, yes, yes.
Okay.
Groundwater goes to hundred of years.
Yes. Oh, sorry. What is happening? Okay. 22 days. Then again, yes, you are right. Global groundwater, it may be having of something, maybe 250 of years. It may go up to this. Okay, but for the
Hmm.
ocean, you will get some value of something in round figure. You will get a value of something 500 years. You can compute it easily, not an issue based on our previous concept that we discussed in our previous assignment session. So you will get this idea. So definitely ocean will be following in the first number, then followed by global groundwater, then river, then atmospheric vapor, right?
Hmm. Hmm.
Okay. Now, yeah, the earlier concepts only that how we were calculating at that time, but you have to notice one thing, like there is a one line. I have also reminded in our previous session that if there is a short residence time for the moisture in the atmosphere exist, okay, then
Hmm.
we can say that we don't have a sufficient time, okay, to predict that how that particular moisture will behave. Like for an example, if we are saying that extreme kind of precipitation is happening in a particular region, right? So definitely its intensity will be high, okay, its intensity will be high and duration will be very low, okay. So if duration is
Hmm.
very low, then definitely whatever the water it is coming and whatever the outflow it is generating in form of flood, okay, so it will be very quick, right? It will be very quick, and that is why we can't predict that how much of water in terms of discharge it is getting uh, out of that area. We cannot predict, and due to this, whatever the design of any kind of structure we make, it is not always we can say that 100% truly always therefore we always use a word probability, okay. So that the thing is like, if we are having a low residence time value, then we cannot predict the movement of that particular particle, or maybe a this one water movement, okay, from one phase to another phase. So here it is mentioned that we cannot forecast accurately. This is the thing I want to mention. If there is a low residence time for the moisture, then we cannot forecast the possible movement of water in that particular area. Okay, got it? You can relate it with the flood that we got, maybe it within I guess within a second flood can pass through a region, okay, and we cannot control that, right? Okay. So the same thing, I just added this slide to remind you that TR value will be 8.2 if we are counting the atmospheric water. Then TR value will be 22.2 days if we are counting the river water. Like it will be a surface runoff. And then again, in similar way, you can also compute this groundwater, and we can also compute whatever the ocean we are taking. So for the ocean, you can take the entire value, like total runoff you have to take here, and in this case, you have to take the volume of this much value. Okay, I'm moving ahead. So now coming to the numerical questions. Okay. So Ashish, now we like firstly I want both of you to go through this, because you have already went through the lectures and you already have formulas, you have already have a few things in your mind, and try to figure out the what could be the possible answer of this. Then we will discuss it later. Okay. So go through it first. So raindrop of different size are carried by a air current that is traveling vertically upward at a velocity of 4.55 meter per second. Density of water is given, it is 998, and density of air it is given 1.2 kg per meter cube. Velocity it is asking, okay, and what could be the diameter of a drop? It is saying 2.17 mm. So we are having the data of density of water. So it is rho of W, that is equal to 998 kg per meter cube. It is saying rho of A 1.2 kg per meter cube. Then it is saying that we have a diameter value. It is saying 2.17 mm. Based on this we have to go. There is one more thing, it is mentioned that the velocity of air it is saying, okay, it is saying 4.55 meter per second. So Ashish,
we need to use terminal velocity formula over here, no?
yeah, firstly let me know why you are choosing this one, terminal velocity concept. Like,
Because
yes, tell me.
yeah, because terminal velocity is the velocity where the forces came to the equilibrium. It is a constant velocity once it reaches the constant velocity.
Yes, good one.
If a drop dropping from the west, it attain a particular velocity and then it remain constant. That velocity
Yes.
is the terminal velocity.
Okay, so firstly, you are right. So whenever the terminal velocity we are using, so definitely it is having some kind of media. Okay, right? So here the medium is what? It is an air medium. So here the
Yes.
atmospheric precipitation is happening in the media that is called air. So the water drops are falling now, and whatever the friction or maybe a obstruction we can say, or maybe a resistance it will found, so it will be coming from the air media only. Okay, so the resistance will be there. So based on that we are having a concept called Stokes law, right? So based on the Stokes law we are using this to figure out that what could be the possible velocity of that drop. So it will be a net velocity only, right? Why it is net? Because there will be a gravity force, it will be acting, okay, and there will be simultaneously buoyancy force as well as the drag force will be acting on that drop, right? Got it or not?
Hmm.
Yes. So
Got it.
you are right that we have to use the terminal velocity concept. You are right, go ahead. So the terminal velocity formula, you may be remembering this, like square root of 4 by 3 g into d upon drag coefficient, that is, sorry, that is CD and
4
then
by 3 G.
rho w upon rho a minus 1. Got it? So we are using this formula.
Mhm.
So
Yeah, correct.
for this g value, g is the acceleration due to gravity, which is acting on that water drop. So it will be 9.81 meter per second square, right? And then coming
Hmm.
to dia value, so d will be what? It will be 2.17 into 10 to the power of minus 3 in terms of meter. We are converting all the units in SI units, right?
Mhm.
Yes. And then one more thing I want to add, like for that CD value, okay,
Mhm.
there is certain kind of like a table already provided by some researchers, okay. So here what you have to use, like I want to show you that table. So firstly go through this table, okay. This table
Ah.
have been taken from VT Chow book, okay. So they have already mentioned the source, that from where they have taken this table, okay, Mason 1957. So they have shown that how the drag coefficient will vary based on the drop diameter. So here what we are having a drop of something kind of 2.17, right? It will come fall between 2 to 3 mm, right? So that is why I have selected the value of approximately CD is something 0.510. You can, it is not a random, it is just a linear interpolation, okay. We have got this value based on the linear interpolation, okay. You may be knowing this, I guess, y2 minus y1 equal to m x2 minus x1. This is a concept that has been used here. So we are predicting the y2 value. So y2 value here, it is CD only. CD is 0.510. So what you will
Could you
take?
could you please repeat it?
Okay. So
Yeah.
how we are determining the CD value? Though Ashish, firstly I want to mention that definitely whenever these questions will be coming, drag coefficient will be provided to you only. Okay, it will be
Okay.
directly mentioned in the questions. But if it is
Mhm.
not there, then definitely they may be providing some kind of table. Okay,
Mhm.
so this table could be an assistant kind of thing. From there you can get
Mhm.
the value. So now what they are showing the variation of drag coefficient, that is CD value, based on the drop diameter, okay. Like how the drag coefficient value it is mentioned, this is a standard table. Like if you are having in the question, if you are having directly value of 2 mm, 2 mm dia, it is given in the question. For this
Mhm.
question you have 2.17 value, right?
Mhm.
So you can directly take this value 0.5 0.517, got it.
Mhm.
But if your dia value is lying between somewhat 2 to 3, they, like for an example, here you are getting the value of like d equal to 2.17 mm, okay.
Mhm.
So it is falling between them. So what you have to see, you have to just consider this like a linear variation, like whatever the graph it is showing, it is having a linear variation kind of thing,
Mhm.
okay. Like there is a relation, like maybe in your mathematics, in your like 10th or 11th, you may have studied this, like y equal to mx kind of thing. Whenever these particular equation fit, it is
Mhm.
a just a linear graph, okay.
Mhm.
So what is here, what is the y value here? So y, it will be a CD, and what is x? It will be a diameter, your dia value, okay. So this will be a graph like this, CD versus
Mhm.
this one, like D.
Diameter.
Yes. So what I'm just saying that if we are having 2 points on this line, then how we can predict a value, like unknown value. Okay, so now for instance, you are having a value of 2, so in the dia, okay, right, in the dia you are having value of 2, so it will be a 2 here, then again here it will be like it will be a 3 only, so it will be 3 mm. Okay, and corresponding you will be having a CD value. Got it? What will be a CD value? CD value will be your here
Y1.
yes,
See. Yeah.
0.517, this one, and then if you talk about this one, then definitely you will be having 0.503. Got it?
3. Yeah.
Now
Yes.
you can
Correct.
you know this equation also, like whenever the straight line having two points, okay, like x1 and y1, if there are 2 points lying in the straight line, okay, now you can see you have already have 2 points, x1 y1, and then again
Next
you
to.
have x2 y2. So there is one equation that works, that is what I have mentioned here, y2 minus y1 equal to m into x2 minus x1. That is similar to this only, whatever you this only, what I have done, I have replaced y with y2 minus y1 and x with x2 minus x1. Got it? Got it, Ashish?
Yeah, I got it.
And what about the m value? So m is just a it is a slope,
Slope.
so you
Yeah. Yeah.
already know the m value, that it is already a y2 minus y1 upon x2 minus x1. It is m value. So from this you can get this value, but this is just a calculation procedure. But from the, like if you are like lacking with the time, you are like you are only having a seconds, that how we are just getting the value. So definitely 2.17 will be lying between 2 to 3. So definitely your value will be this drag coefficient value will be between 0.517 and 0.503. Got it? So definitely it will be somewhat around 0.510, which you can get from this equation, what I mentioned here. Got it? So for
Got it.
this
Got it.
calculation, you can take the CD value as 0.510 and go ahead. So now, if we back with the things, so now CD we are having equal to 0.510. It will be a dimensionless value, you know this, because it is a coefficient, so it will be unitless. Now if we want to know the value like rho of W, so can you tell me that density of water?
One
It is
1,000
already no,
kilogram.
if it is in
Oh,
terms of kg, you are saying when one value it is in like one, it will be in gram per cc.
well, CCC.
Got it?
1,000 kilogram per meter cube
Yes,
is it?
so in the question itself they have provided 998. Okay, so
Hmm.
we will be using this only. And now what about what thing left? It is rho a. So what rho
Uh,
a is here, they also
1.2.
provided, oh yes, 1.2. Got it? So based on this, what value you are getting now, tell me. Put all those values.
Uh, just a minute. 1.33
Let
into.
me see whether Balamurugan got or not. Okay,
0.
I'm discarding this. Okay, so Balamurugan 22 30 days here, river. Okay, yes, good. Yes, Balamurugan, for groundwater, I guess it won't be reach up to 1,000 years. Yeah, definitely it will be of around 250 to 300 years. For the ocean, you can calculate from the table. You can get these things. Like from my calculation, I got the ocean value of somewhat 560 years. Okay. Now, what is the another thing is that Balamurugan, you have got I guess estimated 4.856. What you are saying? 4.5. It's an answer or something? Balamurugan, can you tell me? 4. I guess velocity of air current it is mentioned. Answer for the velocity. Okay, okay. Okay, good. Ashish,
Yeah.
what is your answer? Like, is it matching with the
No,
Balamurgan or not?
1 minute. I need to reconsider.
Uh, Balamurgan, I want to mention one thing that you can see, I guess, 4 point what happened to the velocity of air. 4 point. Yes, this is only just for an idea. There is nothing to do with velocity of air. It is just only for the comparison, like whether whatever the velocity water drop is falling, है ना? It is just for the comparison with the velocity of air. Velocity of air will be in upward direction only, so it is just for the comparison. Okay, but if the drop is falling, then definitely it will be having more velocity as compared to velocity of air, then only water can fall. Got it? So I guess Bala Murugan, what happened to the velocity of air? Yes, upward direction oppose the drop. Yes, you are right. So definitely there is some kind of a positive or negative sign we have to mention in that case. Yes. Okay. Ashish,
Yes.
why you are getting late? Only you have to put the values only. I guess this formula is wrong. Okay, Ashish, firstly I want to
Hmm.
mention one thing. This formula is wrong. You can see that 0.5 it will be in
Oh,
entirely
yes, yes, yes.
right. So
Yeah, that.
you have to make me like
No,
whenever
no. No.
I may
Hmm.
also make some mistakes, right? So you can see now that this entire square root will be in the entire formula. Got it?
Hmm.
Yes, I forgot to put this bracket. That is why I guess Balamurgan, you may be getting some kind of lower value. 4.8 is, I guess, it is somewhat low as compared to what I expect from this. Meanwhile, I can also compute this from my yes, Kelsey. Answer, Ashish, tell me the answer. Then only I
Yeah,
can.
I'm computing it.
Okay,
Just
good,
give
good.
me a minute.
Go ahead. Yes, I'm getting the same like what is mentioned here na. This value I'm getting the same, but I want you people to get this answer. Otherwise, there may be some discrepancy also. We can discuss.
Yes, sir.
Okay, from the above formula, I got this correct only. Good, good, Balagungan. Right.
1 minute. What is G over here?
Ashish, like there will be a requirement of scientific calculator based on that. Otherwise, you will
Yes,
be
yes.
having too
Actually,
much.
I missed my calculator at my home today.
No, no,
So,
no, not an issue.
yeah.
Okay, you can take your time.
Can you show me the values you put? Just the
Ha ha ha.
values.
Yes, I'm just showing you.
So for row W we put 998, for
Right,
row
yes,
A 1.2,
yes,
G is 9.81,
right,
D is 2.17.
into 10 to the power minus 3.
Oh, I did this mistake.
Ah,
Yeah,
yes,
that's
because it will be in meters now. We have to get the
yes,
value,
yes,
VT will be in
yes.
meters per second.
Okay, okay. That mistake I did.
Yes.
Okay. Okay, we can move forward. I'll just
Okay,
check it.
fantastic. I'm moving forward now.
Mhm.
So the next question is again some kind of calculative numerical. So now the question is what is here is that estimate the constant rate of withdrawal. Okay, withdrawal will be in terms of water. So we are withdrawing the water from a 1375 hectare reservoir in a month of 30 days, during which the reservoir level dropped by 0.75 meter. Like what it is saying that within after like within a month of 30 days, what is happening, a reservoir level is getting dropped and it is coming now 0.75 meter. Okay, and now one more thing they are adding, that there is an average inflow at the same time, like in that month only average inflow is also happening into that reservoir, and what value they are getting, it is 0.5 million meter cube per day. Okay, now one more data they are providing. Okay, they are providing that during the month the average seepage loss is also happening. Okay, so water is getting infiltrated into the subsurface area, subsurface zone where the reservoir have been constructed. Okay, so seepage loss is also happening from the reservoir, and they have found that value of something 2.5 centimeter. Okay, so these all values are converted in only in terms of depth only. Got it? So depth of
Mhm.
a water column, you can say. Now one more thing they are saying, that total precipitation they have found it of something 18.5 centimeter, and total evaporation was 9.5 centimeter. So the first thing I want to mention it is that they all are the parameters of water, like hydrological cycle only. Got it? And you know that entire hydrological cycle parameters, they are all a kind of mass balance. Okay, a kind of mass balance thing. Mass balance thing means what? Like you have already learned from Reynolds transport theorem. Okay, that there could be a possibility that continuity equation may exist. Okay, right? Continuity equation may
Mhm.
exist. Continuity in terms of what? You have already learned that whenever the steady state condition exists, then there is always an inflow minus outflow. Okay, that will comes out in terms of change in storage. Do you remember,
Change in
Ashish?
storage. Yes, 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 correct.
Okay, so
S, we say S.
got it. Yes. So inflow minus outflow is change in storage. Now you have to quantify the parameters, that which parameters they are associating, they are contributing towards the inflow, and what are the parameters they are contributing to the outflow. And simultaneously, if you are counting the difference, then definitely there will be certain parameters which are contributing to the storage. Okay. Now firstly you have to tell me from this particular problem that what kind of parameters they could be of inflow type. So firstly tell me the parameters. Inflow means you are getting thing now, like if we are having a
Mhm.
certain kind of
The
reservoir.
precipitation is inflow.
Yes, wait a minute, let me draw this. Okay.
Mhm.
Ha. So this is a reservoir kind of thing. There will be a some kind of water table, and now entire water surface it will be flowing. Okay. So
Mhm.
yes, you tell right that inflow one first one is will be precipitation, right?
Precipitation.
Good one. Then
Withdrawal
simultaneously you
reservoir.
can also quantify the outflow parameters.
The evaporation is outflow and
Yes.
the seepage is outflow.
Okay, good one. So evaporation we have got it. Then we are also getting the seepage loss. It is also counting in terms of outflow. Then other parameters.
The concentrated withdrawal from
Whatever
the
the
withdrawal rate.
good. So we are counting the withdrawal rate. Good one. So
It's
withdrawal,
outflow.
not in terms of withdrawal rate, but yes, withdrawal will be there. Some kind of depth, we know that there is some kind of withdrawal is happening. So yes, withdrawal we have counted. Now there may be some more parameters. They are counting inflow. Like inflow is coming. Like a certain kind of discharge is
Mhm.
coming into that reservoir.
Mhm.
Okay, are you getting the word? Average inflow it is
Yes.
mentioned here. Okay, so it is a discharge, but we can convert it in terms of depth. We will convert it, but meanwhile we can count in terms of average inflow, right? So average inflow is also counted in this. Got it?
Mhm.
Okay. Now the one more thing is there, that it is saying that the reservoir level is dropped by 0.75 meter, okay, within a month. Got it?
Hmm.
So whatever the inflow is happening, okay, whatever the inflow it is coming here, like you can see from here, like inflow is coming here, and then again outflow is going out from here. Got it? But they are
Hmm.
saying that whatever the there is some kind of H value, water level will be there, it is getting depleted now. So we can assume it like there once there will be a water of some kind of 0.75 meter already stored in this reservoir, and now it has been withdrawn.
Mhm.
Okay, it was stored earlier, it was stored. Okay, or you can also say that in this particular aspect it is asking what change in storage, right? So
Mhm.
someone is taking out the water, and then you are seeing the change of 0.7 meter of water level change you are seeing, right? From the word you can
Hmm.
see that level dropped. Got it? So
Hmm.
it is do you think it is representing a change in storage, right? A change in storage, because
Yes.
reservoir water level is changing. Got it?
Mhm. Hmm.
Okay, so now you got the difference, that what parameters will be counted in terms of inflow and what parameters they will be counting in terms of outflow, and ultimately it will be if we are taking a difference, it will be contributing a change in storage. Now comes to the some kind of brief explanation. So firstly I want to mention that all units whatever you are going to take, it will be in terms of depth only. Got it? It will be
Hmm.
in terms of depth. So I want both of you to go with me parallelly, and try to get the depth value, whatever the depth value we are going to figure out. Okay, so firstly Ashish, let me know some of the parameters we already know. Evaporation value, do you know this in terms of depth? So evaporation we have like
Yes.
9.5
Yes. We
centimeter,
have
right?
it. We have.
9.5 centimeter, and we will convert it into a meter only. So it will be coming like
Okay.
0.095, right, in meter. Good. So
Mhm.
we got this
Hmm.
parameter. Now again the second parameter is what? Seepage parameter. So seepage parameter will be what? How much
Uh,
seepage loss is happening?
Two
It is
point.
of about 2.5 centimeter, right?
0.025.
Yes, good. So 0.025 meter. Now withdrawal we know, we don't know. Do you know this withdrawal value? Do you know this? How much water is getting withdrawal from this reservoir? Do you know this value?
We need to estimate this one.
Yes. So firstly we will be counting, we will be estimating the withdrawal depth. Then we will be calculating, later we will be calculating the rate of withdrawal. Got it?
Mhm.
So
Mhm.
here we are assuming it as Q. Got it? It will be in terms of depth
Okay.
only. It will be in terms of meter. You can assume it.
Hmm.
Now, what else parameters left? Now you already know the change in storage. So change in storage is how much? You know this 0.75 meter. Got it?
Hmm. Hmm.
Okay. Now what are the things left? So we also know the precipitation value. How much
Yeah,
precipitation value is
precipitation
falling?
18.5.
Good. So
18.5
convert it
divided
into
by
this.
100
So
is
0.185.
point 1. Yeah, 0.185.
Okay, it will be in meter. Now comes to average inflow. Now this is there
We,
will be
we, we,
huh.
sorry to interrupt. Withdrawal is Q is discharge now?
not a discharge. We are, I mentioned na, we are whatever the formula is there, we are only applying all the parameters in terms of depth only. Got it?
Okay.
We
Okay.
are
Got it.
all taking the value in terms of meter. Okay,
Hmm.
so now the thing is like now the question come that how we will calculating average inflow in terms of meter. That is a target, because we have to
Hmm.
know that average inflow depth, we have to quantify this. But what we have provided, we have been provided with the discharge. Okay, we are having average inflow discharge, we are having. So it is just kind of, you can say, a q value is there for an average inflow. Got it?
Hmm.
So if we are having a q value, so you may be knowing the thing like q is always equal to what? It will always be, firstly we have to compute entire value, average inflow. So average inflow is what it is saying, 0.5 million meter cube per day. Got it?
Hmm.
So if we convert it, so 0.5 into 10 to the power 6 meter cube per day. But this formula, whatever the other values we are taking, it is for entire month. Do you know this?
Hmm.
Precipitation is for how much? It is for 30 days.
30
Right?
days.
So we have to compute this q value for 30 days also. So we are computing this for 30 days. So you can multiply this in with the 30, and you will, what you will be getting, you will be getting in terms of meter cube. Got it?
Then we need to convert into the
Into,
depth by
yes. So
multiplying, then
what we are
dividing by
doing, what
density.
will be divide, we will be dividing this q by area. Area of
Area.
what? Area of reservoir.
Reservoir.
है ना? And
Hmm.
this area will be converting, we are converting, it is provided in terms of hectare. Okay, but we have to convert it into terms of meter square,
Meter
right?
square.
So
10 to the
there is
power.
some kind of conversion, you know, that 1 hectare is always equal to 10 to the power 4
4
meter square.
meters.
Okay,
Hmm.
so you will keep this value and divide it, and you will get the q value. Now calculate it and tell me the value, that what this value we are getting.
Just a minute.
Take it this as I. This will be I, good one. Okay, I want to know. Tell me. Hmm? I'm not discarding it. I'm keeping this, and let me know. Burgan, Bala Murugan may be replying something. Yes, good. From the formula, okay. Yeah, this one is got it. Reservoir inflow, release from reservoir, good. 0.5, good. Okay, good, fantastic, Balamurugan. You are going in a good way.
वो राजेश का नंबर है?
You can see the screen, and in parallel you can try to figure out that what could be the I value we will be getting.
वो पापा से बात से नहीं हमारे। अरे वो पापा काट रहा
So we get density.
Okay, so what we were focusing on is that like sorry. So I value we want to know in terms of meter, so it will be q by a. Okay, or you can say q of inflow, we have to write in this way, q of inflow upon area. So q inflow is how much value we were getting, so it was of around maybe 5 3 jar. Okay, that will be multiplied in terms of this, so 0.5 into 10 to the power of 6 into 30, it will be in terms of meter cube, divided by 1375 into 10 to the power 4. Got it?
1.09.
Okay, 1.09, good. This will be in terms of meter.
Meter.
Okay. Now the thing is left what, that we have to keep all these things in that formula. So what formula we were having? Inflow minus outflow
Outflow.
is equal to change in storage, that is delta S. So inflow, tell me the values now. Precipitation, firstly tell me the P value, then we will be counting inflow, okay, and then this will be there. Then again we will be subtracting outflow as like firstly we will be putting the value, withdrawal value, that will be in Q, plus we will put evaporation value, then we will put seepage loss, right, Ashish?
Yeah, got it.
Got it. And then
Yeah.
simultaneously you have to put the change in storage. Now tell me the values. P value how much?
P is 0.185.
Okay, 0.185. Then I value, that this
Uh,
one you computed
1.09.
1.09. Then Q is the will be same only. We are figuring out. We will be computing this. Then E value how much?
Evaporation is 0.095.
0.095. Then seepage value how much? 0.25.
0.25. 0.025.
Okay, this is there. Then again you have to keep the value 0. Sorry, yes, 0.75 in meters. Now you can compute the value of Q and let me know how much it is coming.
Just a minute. Q.
Let me see. Bala Murugan will be replying to this. Yes, you are right, Balamurugan. You got the value correctly, 1.091. Yes. Go ahead and try to find out the value of water withdrawal in terms of depth value in meters only. And keep in mind that whatever the values we are computing, it is for entire month. Okay, like it is for the 30 days we are getting. Let me see Balamurugan got or not.
0.405.
0.405. Yes, you are right. Balamurugan, what is your answer? Try to solve the problems parallelly with me. Then you will be finding no difficulty in that. Okay, then I'm moving ahead. Okay, so now you got the value. Q is what? How much? 0.40.
40405.
405. Good. Now what you were asked from that question, it was of about rate of water
Withdrawal.
withdrawal. Okay, So rate of water withdrawal is some kind related to a water in terms of discharge only. Got it?
Mhm.
So what you have to do, you have to compute this rate in unit of meter cube per second. Like it was similar to the inflow. Like you can consider it as a rate of water withdrawal as an outflow. You can consider directly water, like imagine if we are into a hydro or maybe in a reservoir and a dam we are having, and there is a spillway provided. So some kind of sometimes water being spill out by opening the gates, so it will be counted in terms of outflow. So this is a similar thing. Got it?
Mhm.
So now what you have to do, you have to just go with the reverse process, and you have to compute this. So we are having q value, so we know the depth, so we will multiply this q value, it is in terms of meter, so we will multiply with a, and we will divide it by how much. We will be divided in it was earlier I told you that whatever the value you are getting, q value you are getting, it is for the entire 30 days, right? So at the end, for getting the second value, you have to divide it by firstly 30 days, then again every day will be divided in terms of 24 hours, and then again every hour will be divided into 60 minutes, then 60 minutes will be divided in further seconds, that it will be 60 seconds. Got it? And area you already know that 1375 into 10 to the power of 4 meter square. Got it? Put these values and you will find the answer. So it will be counted as outflow discharge. Ashish,
Yes,
you got
yes,
the concept or not?
yeah, I got it.
Okay. So now you can see the final calculation. Okay. So you are right that you got the value of Q as somewhat 0.406. It is for entire 30 days. Then if you want to quantify the rate of withdrawal, so definitely it will be an outflow of having unit meter cube per second. And how you are going to calculate? So this is a depth value you get, and if you are multiplying this one area, and then again you are dividing it by time, whatever the time of things you have been provided. So entirely what you are getting, it will be in terms of second, it will be in terms of meter, so multiply these units, you will be getting this much of answer. Got it? Ashish,
Yeah, I got
clear or
it. I
not?
got it.
Okay, let me see Balamurgan's reply, then we will move ahead. Okay, starting it. Okay, please find 0.75 is negative, sir, because drop in water level, sir. So got some other answer, please, sir. Okay. Firstly, Balamurgan, I want to mention one thing, that storage is not a it is not an initial or maybe a final value. We are considering a change. Okay, so whenever the change we are taking, it is a change value, like whatever the thing it is mentioned, like 0.75. okay, in the question itself it is mentioned that 0.75 meter of water level is being dropped, so it is just a change, so it is just a delta s. How delta s has been calculated? So it may be calculated in terms of you can see, like if there may be a reservoir, so definitely there may be at the start, at the beginning, there may be some kind of water level starting at the initial stage, so you can take it as water at initial. Okay, and then someone have been spilled out some amount of water. Okay, and now the water have been come up to this one. So how you will be designated it as? It will be as like water level final, you can say like this. So water initial minus water final, the difference of it is considered as 0.75. Okay, and this is counted as a change in storage. It is called a change in storage. So there won't be a kind of confusion with the sign. Okay. Balamurugan, is it clear? Rise of water should be positive. Yes. So at the initial, as I mentioned, that if you are considering water level at initial, so definitely it will be a value having positive sign. Then final, so some kind of some amount of water is being passed on, or maybe moving from the reservoir, so we are taking it as negative. So it will be coming in positive only now. If the difference is there, we are taking an initial and a final value, so it will be coming in 0.75. It will be having a sign of plus only. Balamurugan, it is just a change of storage. Don't confuse with this. It is just a confusion with the words only. Like it is being dropped. So now there may be a water level at the initial having certain magnitude. Then some amount of Q water have been spilled out, and then there may be some fixed final water level will be there, and the difference it is mentioned that 0.75 meter of difference is there. Balamurugan, should we move ahead now? Okay, thank you. Okay, so I'm going back to my screen again. Okay, so it is now clear. Now coming to the next question. So again, now we are jumping into the precipitable water, or maybe you can say atmospheric water, where we are dealing with the water vapor, humidity, okay, and even air density we will be calculating in further questions. So the question here is what? If the air temperature, okay, it is talking about the atmospheric air. So atmospheric air temperature is 18 degrees Celsius and relative humidity it is mentioned of 40%. At the same time, it is mentioned that atmospheric pressure, okay, this atmospheric pressure is 100 kilopascal. And they have provided RA value. RA value is what? That is a gas constant value. Okay. So they have provided a gas constant value, whatever the air is there, and at this now what they are asking to compute the vapor pressure that will be applied by this air. Like if we are having a ground, okay, we are having a ground, there may be a certain kind of this much of atmospheric air influence may be there. So airs are there now, you know this. Now how much pressure it will be exerted into this, okay, so we have to figure it out. A vapor pressure exerted by the air, and definitely this it is not just a air, it is not a dry air. Definitely whatever the vapor pressure it is being exerted, it will be just by a moist air, it will be a moisture air, right? Got it? So there may be, it is mentioned that relative humidity is also here. So you might have heard what is the relative humidity is. Relative humidity is always defined as a ratio of vapor pressure of moist air with reference to
Atmospheric pressure.
no
E by
with
P.
vapor pressure at the saturation level.
Okay, yeah.
E by ES,
E by S. Okay.
right? So And do you know the physical meaning of this? Like this one, saturated vapor pressure. What do you mean by this?
Yeah, it is the maximum level of water that the atmosphere can contain.
Yes, maximum level, not a maximum level of water, but yes, maximum moisture.
Moisture, yeah.
Yes, so maximum
Capacity.
moisture it can hold, this air can hold. Okay, and what about this? E. So E is a vapor pressure, okay, of that air, vapor pressure of that air, okay, at a specific temperature, right? At any specific temperature it may be. Definitely, we are also computing this saturated vapor pressure at a specific temperature only, but sometimes whatever the vapor pressure we are computing, this is an actual vapor pressure, okay? Don't confuse with this actual vapor pressure. And sometimes uh, this actual vapor pressure, this may start at a due temperature point. So like can you try to compute this? So now whatever the data you have, so we are having air temperature, so you can write it as T of air 18 degrees Celsius. Relative humidity it has been provided, it is of 40%, you can convert it as 0.4, and it is the ratio of E by Es. Now they have also provided a P value, that is a pressure, okay, atmospheric pressure it can exert, so kPa. Now RA value has also been given, 289 joule per kg and Kelvin. Now they want to know the value of E, okay? Ashish, got it or not?
Yeah.
They want to compute, they want us to compute the value of E. So for this computation we need if we get this value es value if we get, so definitely
Yeah.
by multiplying this value with 0.4 we will get the value of E. Don't
It's
compute
0.80. Yeah, yeah.
what
The ES value is, I had calculated it. It's 2.022 kilopascal.
0 point, how you have calculated this value? Yes.
Yes, I have applied the formula, the 611 exponential of 17.271 plus
Good,
237.3
good.
plus.
Yes,
Yeah.
that is the formula we have to use.
Huh.
So wait a minute. Okay. Okay. So just a few concepts only, that how we are going to relate everything. So for your reference, RH have been mentioned, that RH is the ratio of actual vapor pressure to the saturation value at a given air temperature. Okay, we have already discussed this.
Mhm.
Then saturated vapor pressure, what is there? Ashish, you are right that maximum moisture content air can hold. Definitely, you are right now. Again, the thing is like this is all about E, that how we can compute it, but it is not always true that E will be defined at TD. Basically what is meant by this due temperature is that whenever we are computing, we are about to compute ES value, so starting value, that at what temperature ES will start, like saturation value may start. So just for the reference, due value will be taken. So from this graph you can see that for the TD value we are getting this E, and then if we are increasing this, then at certain, like if we are going beyond 20 degrees Celsius, then saturation of that air will start, okay, of not a air, don't confuse with this, it will be a moist air only, because if you are talking a air, then definitely sometimes we can use we can have in mind that it may be a dry air also, but no, if you are talking about atmospheric air, then definitely it will be moist only, moisture will be there, okay.
Mhm.
So now the thing is like you can see that air temperature we got the RH value 0.4, we know the concept that RH, the ratio of this, So actual vapor pressure is E, then saturated vapor pressure is this, and now you can see the ES value, how we are calculating. So saturated vapor pressure can be calculated by using the formula 611 e to the power 17.27 T and plus this temperature will be added with the 237.3 as a constant value. Okay. So how much value you were be getting, Ashish?
Yeah, I was getting 2.04
You will be
kilopascal.
kilopascal, right. Good one. So 0.2064 7 kPa. Good. Now it multiply it with 0.4. How much you are getting?
Point 4, no? 0.826,
Yes.
yes, correct.
So this is an answer. Okay.
Mhm.
Let me see. Balamurugan. Okay. Balamurugan, any reply to this question? Should I share my screen, then you can get the values? Asif, we can wait for 1 minute, then we will start. We will go with the next question. Okay.
Sure.
Yeah.
Yeah, he got to a 0.8218.
Okay. Then okay. I should move ahead now. So the next question is again the things are much more going in the atmospheric air only. Okay, now the question is asking about specific humidity. Okay, in the previous question we were having some value related to relative humidity, but now we are concerned with the specific humidity. Okay, but now also they have provided relative humidity value. Keep in mind, and the atmospheric pressure is also there. Ashish, I want to know one thing. That do you know that where, like, what is the reference of atmospheric pressure? Like sometimes you might have heard that whenever the RL value we are calculating, like for constructing any kind of structure, we should know the reduced level, right? Do you know this word?
I know RL.
Okay, so for this we take some kind of reference. Can you tell me the name of that?
HFL.
No. RL may be like if you are not a, HFL, but it may be a mean sea level, MSL. Have you heard of
Hmm.
this?
Yes, I
So
know.
it is the reference from here we consider it as RL, we consider it as 0.
Hmm.
Okay, and then we take other values in reference to this. So in
Hmm.
similar way, atmospheric pressure is also taken from MSL. Like at the atmospheric pressure, I guess at the this MSL, we used to take 1 into 10 to the power, or maybe 1.01 into 10 to the power of 5. Okay, Pascal. I'm just for the your knowledge only. I'm
Could you please repeat that 1.01, how it came?
It's a standard value
Hmm.
that atmospheric pressure,
Okay.
okay, at the MSL, like mean sea level, we are taking it as 1.01 into 10 to the power 5 Pascal. It is a reference value. Okay, it is in Pascal. Okay, if we convert in terms of kilopascal, then what value will be getting? I guess 100
1.01 into 10 to the power 2.
100 into 100 kilopascal, right?
Hmm.
101 maybe, right? So you
Okay.
can see that MSL, at the MSL we are having this value, but if we are going in our inland area, like in our city or maybe something, then definitely this atmospheric pressure value will be changing accordingly. Got it?
Hmm.
Because this atmospheric pressure will be varying with the with altitude now. Do you know this? It's kind of pressure now. Pressure is always what we compute, rho g h, right? Rho w g h. So atmospheric pressure will be varying
Hmm.
with the altitude. So just for the information, now we can proceed.
Hmm.
So now Ta we have, that is of 20 degrees Celsius. R H we have again, that is 0.4, that is equal to, you can write the formulas also, E upon ES. Now atmospheric pressure we have, so we can write it as 100 kilopascal. Now RA again they have provided, it is of about 289 joule kg Kelvin. Specific humidity is how much? They are asking. So you may remember that what is the representation of specific humidity. So specific humidity is represented by QE. Now we have to compute that. So firstly, before going to this, I already mentioned everything. Now calculation will be from your side, but let's go with some of the few maybe concept behind this. So you can see specific humidity. So what is it is representing? So it is representing a moisture in overall volume of moist air. So it is just representing a total moisture. Okay. Now it is a measure of moisture content in the atmosphere that got it. So total moisture we can compute by specific humidity. Got it? So what they have mentioned, that QV will be a ratio of density of water vapor to the density of moist air. Now to differentiate this, see this line particular. Whenever we are talking about the density of moist air, so density, don't confuse with PA. PA is basically a rho A. It is a rho A. Okay. So rho A is the sum of densities of dry air as well as the water vapor. This is the thing. Okay. So if they are talking about this one, rho A. So they are talking about this one. So this rho A will be a sum of density, dry density plus what? This will be
moist density.
Water vapor density. So this is the thing. And now this you already got this rho V. Rho V will be what? It will be a density of water vapor only. What we have mentioned, this one. Got it? So this is not a direct formula, because whatever the things they have provided, they have input, whatever the input data we have, it is not directly in use with this formula. So we have to adjust, like we have to substitute some values. So for this substitution only, this rho A will be substituted by this particular aspect. And one more thing, like you can see RV. RV is what? This is a gas constant for water vapor. This will be substituted by gas constant at dry temperature, dry air divided by 0.622. So whatever the formula you are getting now, some kind of 0.622, one numerical part is seen. So it is basically a conversion of gas constant value. So you are getting this particular 0.622. Okay. Got it? And now after putting these particular both the formulas in this particular
RA is equal to RD by 0.622.
Yes, exactly. So it is mentioned also, the gas constant for water vapor is RV equal to RD by this, where 0.622 is the ratio of molecular weight of water vapor to the molecular weight of dry air. It is mentioned. Let me erase this thing so you can view this clearly. So Ashish, the thing is like we have to use these particular formulas in order to get this particular formula. Now one more thing I want to mention, there has apart from these particular two formulas, there is one more formula that is called, you know, that ideal gas equation. You know this gas equation?
PV is equal to NRT.
Yes, PV equal to NRT, right? So NRT. So this particular aspect, this P, it has been taken from this particular formula. So there is some kind of substitution are there. I am not going into the detail, but yes, they are using these three things, and they are finally arriving at this particular formula, that is QV equal to 0.622 e to the power P. Got it? Now for getting we have to compute this particular QV from this only. So we need two input data. That is one is like P. The P is the atmospheric pressure only, right? So we have been
Hmm.
provided this value. Atmospheric pressure value we have P equal to 100 kilopascal, right? So what else we need?
Hmm.
What we need actual this one actual vapor pressure of moist air. We need this. And how we can get this? We can get by using this particular formula. So for getting this, we have RH value. We can compute ES based on temperature value, and we can get the value of E. Firstly, we will be getting E value. Then we will substitute this in this formula, and we will get the QV value. Ashish, got the
Okay,
things or not?
oh yeah, I got it. We multiply ES by RS to get the E.
Right, right. Yes. So firstly do this and try to find out the value of E.
Yeah, so 0.240 2 RH or is to is into okay 0.4 into
Okay, Balamurgan got the value. It is of about, yes, good. Good. Good, Balamurgan, good. Go ahead. 935. I will show you the values later. Maybe yes, how much you are getting. That is E value you
is
got now.
into RH.
So 0 point, yes, you are right, I guess. How much? Yes, 935. 935 approximately, yes, right. So you are getting in Pascal. QV you got it. How much you got it? 0.00582. So QV 0 point how much?
ES is
5.
equal
Yes, approximately you
to
are right. Balamurgan, good job. You got the answer. And one more thing I want to say that yes, you are right that QV maybe it is a dimensionless quantity, but still you should know the things that yes, it is talking about kg in kg of water. That this much kg of moisture is is uh, is present in the moist air that is existing in the atmosphere. So it is just telling you the idea that how much, like it is a total moisture. It is just justifying the thing that how much total moisture is present in the moist air which is present in the atmosphere. Got it? So you have to keep this particular unit in mind. So you will be having some idea that what is the significance of QV. Just getting the values or maybe a magnitude is not sufficient. We should know that yes, definitely it is having a dimensionless quantity, but why? So what is it is representing? So it is representing the total moisture in particular in the certain or maybe defined magnitude of mass of moist air. Ashish,
yes.
how much answer, how much result you got? Like what is the magnitude? Tell me.
No,
Calculate it. I'm not going to forward to the next question. I'm not going to. Okay. Firstly, you have to calculate. You should get the value. Otherwise, there won't be importance of this attending this session, right?
Mhm.
So firstly, calculate the E value.
Yeah, I got ES 2339 Pascal.
Okay, good. So yes, convert. It will be in.
In
Yes, you are right.
yeah,
Now
so
compute
2
QV value.
2.3 and 2.4. It's 2.39 and 2.4. 0.9356. Okay,
Point nine three
93,
five. Yes, you got it.
936, yeah.
RH is right. Yes, good. E value you got it.
0.936. So 0.622 into E is 0.936. And pressure, I have to divide it. Pressure is, we say, 100. So into 0.622. 0.006. Yeah, correct.
Good, good, well done. Now I move forward,
Kilogram.
right? Should I go?
Yeah.
Okay. So I guess only two questions are left now. So this is a one question. So go through it. Like the question is like they are providing some input data like air temperature they have provided in this question, relative humidity you have, atmospheric pressure you have, even now they at the same time gas constant value is there. Now you are required to find out the density of air. Now they are asking about rho A. We know rho W, right? Don't confuse with this. Rho W is a density of water, mass density of water. But now they are asking about mass density of air. So mass density of air we can compute using what? It could be computed by using the ideal gas equation.
PV NRT. Rho
Yes,
V NRT.
ideal gas equation, but it won't be in direct term like
Mhm.
PV equal to nRT, you are right, but now we have to make some modification in this. Okay, right, like volume we can make, what we can make volume, how we can write it as volume will be
Uh, 1 minute.
mass per unit volume is always equal to a density, right?
Mhm.
So we will replace this. Okay.
So rho is equal to P upon RAT.
Yes. So rho A, for getting this, m we know, sorry, m is there. Now this volume value we will take it as n r t. Okay, and it will be divided by p, right? Am I right?
Hmm. Hmm.
Okay. Now m by n is somewhat, it is getting 1. Okay, because n is just a mole, number of moles,
Hmm.
and m. So I guess the thing is basic relation is that P upon RT. You may be knowing this.
Hmm.
Have you got this or not? Like on this you can
Yes.
see. Okay.
Yeah, I got
What is the
answer.
main
1.1.
objective? Objective of this is that how it has been derived. It has been derived by using a gas equation. So now what we have to do, we have to see the P value. So P atmospheric pressure we know, gas constant value we have to know, and then temperature. But keep in mind that temperature, we whatever the temperature value we are going to take in this, it will be in terms of Kelvin. Okay.
Hmm.
So as he is, one more
Yes.
thing I want to mention that there may be certain questions where some other parameters value may be provided, but they may of no use at that particular question, right? Like in this case, you can see that there is no use of relative humidity. RH is also
Hmm.
having no use.
Hmm. Hmm.
At one question, that terminal velocity Vt, we were having Va air. It is
Hmm.
also of no use. It is just having some idea that yes, air is moving in this, and how the water drop will be falling like.
Hmm.
Now get this value and let me know.
Yeah, I got it. It's 1.180
Okay,
kilogram per
okay.
meter.
Let me see. Kelvin conversion 237.3. Okay, I may be wrong in that case.
293 is correct.
273, it is not there.
Yeah, it's correct. 273 plus 20.
So
Correct.
what Balamurugan is saying, I'm not getting that. Mm, Balamurugan, please check. I guess when we are converting degree in Kelvin, I guess we have to add up with 273 only. Please check. Balamurugan, should I move ahead? Ashish, if he is replying, let me know. Meanwhile, I am moving ahead to the next question. Okay, so now you are having one important question in that we have to employ every parameter now, and we have to compute final precipitable water. Okay, so what they have provided us some basic input data, so precipitable water, and now they have particularly defined a region. So you can take a kind of you can say a ground surface. It is having an area of somewhat 1 meter square. So somewhere it has been mentioned 1 meter square of ground surface. Now there they are asking that if I extend this, sorry, sometimes when I am using this now, my drawing get worse and worse. Sorry. Okay. Take the pen also. Okay. So consider it as a just kind of column. Okay. Column in the sense there may be a atmospheric air is there, right? Atmospheric air is there, and what is its height? It is of some kind of 10 kilometers. Got it? And they are also saying that surface pressure, keep in mind, Ashish, that it is of this one, like this is a ground surface GS. So they are talking about this. So pressure at ground surface, they are saying it is of 101.3 kilopascal. At the same time, they are also providing the surface air temperature, like temperature at ground surface. So it is initially 300 degree Celsius. I guess it is not 300 degree, it should be 30. Don't confuse with this. Okay, it will be 30, no, not try to remove this 30 degrees Celsius, because 300 degrees Celsius is just like a steam kind of thing, right? It is not going to possible. But yes, one more thing is it is mentioned that lapse rate. So once the air which is present nearby the ground surface, okay, and if there is certain kind of temperature variation is there, you already know, Ashish, you know that at the ground surface temperature will be at maximum. Like if we are considering 30 degrees Celsius, definitely it will be there. But as we move upward in our atmosphere, temperature is going to decrease or increase? Decrease, right? So temperature at any instant, temperature may be like minus 15 something, 15 degrees Celsius also, because at that time only there is some kind of freezing maybe take place. Sometimes you know that hails kinds of precipitation also exist in our area, right? Why is it there? Because temperature may reach up to minus also. So that is why the things may occur in that case. So the thing is that temperature variation will be occurring. Like now, if the temperature variation is there, then what is the rate? That how heat may be changing. So how it is changing? So with the kilometers or maybe with the height, how it is changing? They have provided the value like 6.5 degrees Celsius per kilometer. Got it? Now, for this particular case, they have also provided the gas constant value. Okay, and also they have just mentioned that we cannot if we are computing a single value by taking 10 kilometer as once, so then definitely it won't be an accurate one. So they are suggesting us to divide this particular column in some kind of grid work. Okay, in form of grids. So divide in this, and whatever the value, firstly compute this value, this one, and then again compute for this one, and then again compute for this one, and compute this one, and then add up all these things, and then try to compute the things. So their aim is this. So delta Z is just like a difference in the elevation. So they are talking that within 10 kilometers, take it as 2 kilometers interval. Got it? Okay. Now, how we are going to approach? So, approach for getting this. Firstly, see that what are the data we have. So, from the question itself, you got this. So, kindly note it down that what are the things we have. So, 10 kilometers of water column height is there. Then air temperature they have provided is that 30 degrees Celsius. Then surface pressure they have given at the ground surface. Also lapse rate they have provided. But for their computation part, or for our computation part, we can convert kilometer in terms of meter. So we have just we have to do, we have to just divide it by 1000. So 6.5 will be divided by 1000. So we are getting 0.065 degrees Celsius per meter. Now again the target ground surface area, just we have discussed in the previous picture. So they are just concerned about this particular office strip, 1 meter of square. Okay. This is a ground surface, and now they have a gas constant of something. Now Ashish, now do you have any idea like how we can approach, like we are targeting the precipitable water, okay, and it will be in terms of mm. Do you have any idea how we can determine this?
First, we need to calculate the pressure at elevation 1 meter.
Okay.
What is the pressure we need to calculate? Yeah, 2 meter, 2 kilometer. Sorry,
Yes, we
P2
can.
at 2 kilometer.
Good.
Then temperature T2 at 2 kilometer.
Good.
Then we need to find out the air density.
Okay.
No, yeah, air density rho 2. Yes, correct. At
Okay.
2 kilometer. Then we need to average it.
Okay.
Same we need to do it for
Every strip, right?
every strip. Yes,
Okay,
yes,
and then
yes.
we have to cumulatively add up all these things, and then we can go ahead, right?
Get them. Yes, yes, yes. Correct.
Yes. So wait a minute. Let me see. Bala Murugan. Okay, pressure at 200 meter each. Yes. Okay. I'm going ahead now. Good. Okay. So, Ashish, you are right. We have to go in some kind of tabular format. There will be a stepwise calculation. Okay, we have to follow, and then we will get the our equivalent depth of liquid water by using this formula. So this is MP. MP is what? Mass of the
Mass.
precipitable water. How much total mass of precipitated water is there? Like it will be in form of condensed water, right? So how much it is there? So how we are calculating this? We are calculating it using change in mass of the precipitable water. Change in is what? Like it is for each strip. So that is why they are using change in the mass of precipitable water. And for every strip, once they get the this particular incremental mass, you can also say. So once they get the incremental mass, we will add up those values, and then accordingly we can compute equivalent depth. Now what is the calculation formula for this? Is that we are multiplying this specific humidity. Got it, Ashish? This is
Yeah.
this is a specific humidity, right? QV,
Mm.
average of specific humidity,
Mm-hmm.
and then we are multiplying it with air density,
Density.
mass of air density. Oh, sorry, mass air density, and then we are also multiplying it with area. Area means what? That how much area it is there. So we are confined with 1 meter square only. So area will be same. Delta Z we know, for each strip we have to take delta Z of some kind of 200 meter or maybe 2 kilometers. Okay. So now our target is we have to compute QV and rho A. This is the main task. And once we will getting the incremental mass of the precipitable water, and based on that we will at the last, for getting the equivalent depth of liquid water, we have to use the formula like volume and mass, you know this rho of water, okay, that is equal to mass per unit volume. Do you know this? And what is volume? Volume is just the area into equivalent depth of liquid water, right or not? So this formula is coming from this only. Ashish,
Yes, correct.
got it or not? It's a simple
Yeah, I got
formula. Rho W is M by V, and volume is replaced by area into H. Okay, so now look at that, come to the table now. So firstly, what it has been like once we have divided the entire atmospheric column in strips, so definitely we are having 0, this is at the ground surface, then 2 kilometers, then 4 kilometers, 6 kilometers, 8 kilometers, 10 kilometers. Now at the ground surface we are having a temperature of 30 degrees Celsius, which have been converted in terms of Kelvin, so it is 303. Now air pressure has been also provided. We also have the value air pressure at the ground. So ground, why ground? Because 0 we are taking, na? So we are at the ground only. Okay. Now density, so rho A. So Ashish, do we have rho A value?
Just a minute.
So I guess rho A we don't have.
We don't have. We have to calculate it.
Okay, so we have to calculate it. So now from this column words, we have to calculate every parameter. So firstly we have to compute density, then vapor pressure we have to take, specific humidity we have to compute, and then we have to average it. We have to simultaneously average the average air density also. Okay, and then we will put this in formula and we will find out the incremental mass. Incremental mass is what? Like at 2 kilometer, how much it is just changing as compared to the ground. So we are computing incremental mass. So now, Ashish, can you tell me that what kind of how we can calculate the density? Just in the previous question, we have computed the density, rho A. We have computed this.
Yep. P upon RAT.
Okay, good. So P upon RAT, right? So do we have P value? Do we have P value?
Yes, we have P value.
What is the P value? See in the this table only, na? You will get the values also. Like if you are
101.3. Yes. 101.3.
101.3. This is an kPa, and then again we are having RA value. RA value is some kind, I guess 287 is there, or 287 joule per kg per Kelvin. Okay, and then again we are having the temperature value. So temperature we need to calculate in terms of Kelvin, right? Because unit will be in Kelvin, right? Got
Yes.
it? Okay, so here we can use this value 303. 303. Now compute this value and tell me whether we are getting this rho A 1.16. Ashish, calculate it.
P upon.
Keep in mind to convert this kilopascal, okay, multiply it with 10 to the power 3 also.
.303. 1.16. Yeah, we got it.
Okay, 1.16, right? Okay, so once we got this, then remember one other problem where we have computed the E value, like actual vapor pressure of moist air, which is present in that atmospheric column, entire column of having area 1 meter square by 10 kilometer. So we have to compute E value. Okay. So how we will get the
Yeah,
E value?
vapor pressure. E upon ES, I
Do
think,
we have
but
any
no,
kind of
no.
other information like now they are having a lapse rate, right? So they are having a
Hmm.
lapse rate. Good, no issue. Okay. So for getting the vapor pressure value, what we can use? Any idea?
We will use the saturation vapor pressure formula.
Okay, so yeah, for saturated vapor pressure, we have T value, right? So we can get the ES value. But what about the
ES
RH?
value.
What about the RH? How we are getting the RH value? Again, the question is
Uh,
there.
we have to put specific humidity. 1 minute.
So wait a minute. You can see that.
Yeah,
Okay.
yeah. This form we need to use the
Okay.
specific formula 0.622 E by P.
Okay. ES we have to directly use. We don't need RH
Mm,
value, na?
no.
Okay, good, good, good. You have to tell me in that way, na? That
Hmm.
why do we need this RH? Because we are
E.
because
Sure.
we need to calculate in already it is mentioned that at the ground we want to calculate it as temperature of 30 degrees Celsius, na?
Hmm.
So we can directly compute at any temperature what could be the vapor pressure. So ES value will be a saturated one, that is representing that yes, at this air temperature what is the vapor pressure. So you are right that ES will be what, 611 e to the power how much, 27.
17.
Okay,
No, no. Yes.
17.3.
17.27
Okay,
T1
T upon 237.
0.3 plus T.
Okay, 237.3 plus T. Yes, by using this. So compute this
Yeah.
and tell me the value whether we are getting this or not.
But
Yes.
here T we need to put in centigrade.
Yes, yes, yes. In centigrade only. Yes. Let me know. Temperature 25 degrees and pressure K given in the problem, sir. Okay, good. Pressure at this QV average. Good. Good. Balamurugan, you are replying. I'm satisfied. Fantastic.
What is
For your
193?
reference, I can show you this. So this is the part that we are concerned with. So we are calculating E value. Okay. So you can see that how much value you are getting for temperature 30 degrees Celsius. Okay. So whatever the raw data we are calculating, this is at the ground surface only till now. Then at the next step, we will calculate it for the 2 kilometers. But this process will be similar. Process will be same.
Mhm.
Got it or not?
Yeah, got it.
How much?
Expansion of 6.
Huh?
611. 20. 10.72.
10.72. Wait a minute. Wait a minute. Let me calculate first. I should also get the value like this. What is the problem? To the power. What is the exponent value you are getting?
1 minute, 5.1,
237.3. It is coming
67.
about 1.94. 1.94.
1.94, yes, yes, correct. 1.94. We need to do exponential of 1.94.
Yes, exponential of right. Do it. I
So
guess
exponential
approximately I am getting the value 40 to 51. Somewhat in my calculator I am getting this value.
1.94 exponential.
Let me check Bala Murugan replied or not. Yes, temperature 20. Okay, Bala Murugan. So I'm just saying that I'm getting this value 40 to 44. I'm getting this like approximately, like not the exact value, but yes, 40 to 51 I'm getting. So we can round it like 4.24 kilopascal. Ashish,
Hmm.
do you got the value or not?
Since I don't have a scientific calculator, I'm facing
Okay,
problem.
okay. I'm assuming that you because of course you got this value na, this how much 1.
Hmm. I got 1.94 because I tried
94.
it.
No issue. Okay.
Yeah.
So exponential of this, it will be of around 6.95. It is coming 6.958, and if we are multiplying by 611, we are getting the value of somewhat approx this one. Okay. So
Hmm.
now I am back to the previous table. So now we got the value of E. Now we are concerned with the QV. So you, Ashish, you may recall the formula QV equal to 0.622, okay, E by P,
E by ES.
right?
Yeah, yeah, E
So
by
we
P.
already have P value, we already have E value, so we can get the QV value, right?
Hmm.
So you can see, for your reference I can say show you this. So what have been done, so E just now we got the value 4.24, this one. Sorry, sorry. Yes. So 4.24, and then pressure, you know that 101.3 it is there in kilopascal. Keep this okay in mind that yes, we are getting in kilopascal. So this is the value we are getting. So 0.026. Yes. So we got this one. Now the thing is that they are next table, next column, it is asking about average increase, average incremental in QV. So definitely we need to calculate for the 2 kilometers now. Okay. So the
Hmm.
similar way we have computed this. So how we got the temperature at 2 kilometers? This is the question now. How we can get this? Because we have been provided at the ground temperature. Okay, we have been provided air pressure at ground only. How we can get the air pressure at 2 kilometer? How we will get the temperature at 2 kilometer? So the question we can solve it by using the formula like this. So this is the first formula, you can see this is a temperature formula. So at Z, okay, at Z equal to 200 meters, okay, above the ground, okay, 2
Hmm.
kilometer above the ground, what will be the temperature? What will be the temperature? What will be the pressure? So we can get the formula by using this. So T1 we know, T1 is what? This is a ground temperature. Alpha we know, alpha is just like lapse rate we have discussed in the previous one. Okay, this much value. Do you remember this, Ashish?
Yes.
Okay, and now
1 0.
Z2 minus Z1. So Z1 will be 0 only. And Z2 will
Hmm.
be what? 200 meters. So all these units in SI only. And keep in mind that whatever the value 17 degrees is coming, we have to add up with the this 270
Hmm.
in order to get the Kelvin value. At the same way, pressure you can also calculate. So the
Hmm.
formula is this. So P2 is always this can be computed in reference to P1 only. But what will the factor you have to multiply? So factor is like this one.
Hmm.
T2 upon T1. Sorry. wait a minute, huh? Okay. Okay, so this is the formula that T2 by T1, and it will be having an exponent of something G upon alpha RA. RA, you know, that is a gas constant value. So now you remember that P1 value we know 101.3, T2 we know, T2 just we have computed this 290, and earlier we were having 30 degree Celsius. So 30 degree if you if we add with 273, we will get somewhat 303, and this G is what? This is the acceleration due to gravity. So 9.81 meter per second square. Okay, and this is alpha, this is RA value, and we are getting the value of P2 now. Okay. Okay, now we already got this. We if we want to calculate the air density at 200, then what else we need to do? If we now Ashish, can you say that at 2000 meter, what will be the pressure and what will be the temperature? It will be this only, na, P2 and T2. Got it?
Yes.
Because at 2000 meter there is value of T2 and P2 only. So we have to keep the P as P2 and T as T2, and we will compute this value. So you can see, wait a minute, there may be some confusion, or maybe it is at the ground only. Keep in mind, the first one it is written at the ground. The next one, if you want to calculate above 2000 meter, so definitely there will be use of 80.4 kPa, okay, divided by RA will be same, and T is what, how much? It is 290. So you will be getting value of 0.97. Okay. Now they were asking about the average value, so average of this you can get. Got it? So now what you got? You get the idea of somewhat this one you got this one, you got this one. Now average out. We have averaged this. We have averaged this also 1.07, na. So you can see, yes, here we are getting 1.0 C. So here we got this value, and now come to the incremental mass, that how we are computing this. So we are computing this by multiplying this column. We are multiplying this column also. Keep in mind, this is an average incremental, so there will be a bar over there. So QV is there, then rho A is there, then what left? A into delta Z, right? So A we know, A is 1 meter square, and delta Z we know, that is also a 2000 meter. So based on that we can get the value of 43.7. You can see here. Now you can see here. This is the calculation part of this. So delta MP you want to quantify, you want to calculate. So we can compute it by putting the value of QV. Okay. So QV, how much QV we got at that time? QV was 0.0205. Ashish. Huh? And then again you can see that what is the rho A value? Rho A value just we got 1.07, and multiplying it by area and multiplying it by delta Z. So we got this value. Now the important thing is that this is for only first strip, and this first strip count only 2000 meters, that is up to 2 kilometers. So we got the value, entire row values for 2 kilometers. Similarly, we have to compute for 4 kilometers, 6 kilometers, 8 kilometers and 10 kilometers. You can see here. Similarly, okay. And once you add up all these delta M, okay, all these delta M you can add, and you will get the total value of 77. How much? 77 kg. Okay. This is for the entire atmospheric column. Got it? Now, last one more thing left. What is there? We have to compute equivalent depth of liquid water. So how we will calculate? So we got the information that yes, for this atmospheric column, how much total mass of the precipitation available. So we got it as 77, right? Now we are dividing it by rho W, that is 1000 kg per meter cube, into area. Area we know 1 meter square. So we are getting the value somewhat in meters, and then again 77 mm. So this much of precipitation can be occurred in that particular atmospheric column. Got it?
Yes,
Now,
I got.
yes, Ashish,
Sorry.
are you telling something?
No, no, I got it.
Okay, one more thing for your additional information, there is one more additional column is there, which is just for your information. What is there? Percentage of total mass. So how we are computing this? 43.7 divided by this one, 77, and multiplying it by
Okay, okay.
100. That is a percentage
Hmm.
formula. So for this 2 kilometer, we are getting that percentage of total mass is there 57%. So you can see that just 2 kilometers above the ground, we are having 57% of total precipitation mass, okay, which
Okay.
is getting accumulated in that district. Now coming to the second district, that is 4 kilometers above the ground. So how much it is coming? It is contributing only 26%. Yes,
26%.
for 6 kilometers it is contributing only 11%.
Hmm.
Then likewise it is at the end you can see 10 kilometers it is only contributing 2%. So now tell me which strip is contributing maximum amount of precipitation in the ground
The
surface.
first trip.
Yes, 2 kilometers area. So now you
Hmm.
got the idea that yes, whatever the moisture which have been trapped in the atmospheric column up to 2 kilometers, they are major contributor of precipitation. Okay.
Hmm.
So this is the thing that have been mentioned in the last note. So the percentage of total mass in each increment shows that more than half of the precipitation water is located in the first 2 kilometer above the land surface in this example. There is only a very small amount of precipitation water above 10 kilometers. Got it? Because 10
Hmm.
kilometers we are only having 2%. So you can not expect that much significant rainfall. Got it?
Hmm.
Okay, so I'm discarding this. Let me see what Bala Murugan, you're replying. Temperature 21, pressure this given in the problem, sir. Yes, good. Bala Murugan, are you completely satisfied with the problem? You got the idea that yes, we have to approach like this. So accordingly, we will end this session also. Like we already got 20 minutes late now. Okay, okay, Bala Murugan. Okay, good. So Ashish, are you like okay with everything? Anything to discuss now?
Yes, yes, yes.
Okay, okay,
No,
okay, Bala.
I'll got everything. Okay, thank you very much.
Okay, okay. We will meet in the next session. Okay.
Sure, sure, sure.
Yeah.